Okay, what we want to look at in this example, it's another example of summing forces and looking at the force body diagrams. But in this one, we want to look at a specific case where the fact that the normal force is not necessarily equal to just gravity. So what we're going to do is we're going to have some big block here. We'll say it's mass 1. And we have some little block over here with mass 2. So let's look at all the forces involved on mass 1. So mass 1 has its own force of gravity, and there's also the force of gravity pushing down on the top of M1, and M1 has a normal force up. So let's sum this. Now, of course, when we're going to sum, we can sum the forces in the x, and that's MAX, and we have the forces in the y, which is MAY. Now, we have no forces drawn moving in the x direction, so this is all 0, and we're good. Now, we'll assume that our block is in equilibrium. And because our block is in equilibrium, that means there's no acceleration because the block is not moving up or moving down. So we can assume that AY is equal to 0. And so because of this, the sum of the forces in the y is 0. And let's look at all the forces we have acting in the y. So when we sum the forces in the y, we have our normal force up, we have Fg down, and we have the force of the red block working down. So we'll write this in the red as well. And the sum of these forces has to equal 0. So what we see is we see that the normal force minus m1g minus m2g has to equal 0. So in this case, the normal force, if we move both of these m1g, m2g over to this side, we see as m1g plus m2g, or the normal force is equal to mass 1 plus mass 2 times g. So in order for the system to stay in equilibrium, the ground has to push up to not only accommodate block 1, but block 2 as well. So this shows that the normal force always isn't equal to just the mass of the one object. In this case, the normal force on this block 1 here is both the mass of M1 and M2.